Okay, let's start with what we covered last time, and we announced that we are going to prove a theorem. And we will prove this with all details because the details are simple than the one that we proved before. And also, we will give two applications among other possibles. The theorem we're going to prove is this one. Suppose that you have U is a solution, global solution of this linear problem in L2. Okay? Hypothesis one. Second, suppose that B is their real values. And you will see that we only use this hypothesis to check that the L2 node of this is preserved. Real value. Such that you can split B in two pieces. B have both real valued. The first piece have this decay. And the second piece satisfies that the support of B2 is contained in the XT you are outside the unit ball, and the radial derivatives, negative part, of this is less than some constant 2. Okay, and we are going to decide if the number should be beta should be 2 alpha or beta should be 4 alpha plus 1 over 3. One of the two. I mean, in the proof we will do it. I couldn't decide when I was doing the proof. Okay, what is A minus means the minimum between A and 0. That means you take the part when this radial derivative is negative, and then you change the sign, and this has to be bounded by some power that we have to decide. Then exists lambda 0 that depend of the L infinity node. Oh, this is bounded, by the way. Of course. You have a bounded this. You are asking for to have this decay, this part, and the other part have this decay. There exists a constant that depends on the L infinity node of C1, of C2, and maybe of alpha, such that if globally you decay like this quantity, then you are 0. Okay, let's start to understand the theorem. where P is equal to 4 minus 3 alpha over 2, I think. 2 alpha over 3. You are trying to establish a relation is how fast the solution decay of this problem accordingly to what is the decay of the potential. Right? Particular case, let's say, particular case. Suppose that alpha is 0. That implies that P is 4/3. Then you say, if I have a bounded potential, the solution of this bounded potential, right, then alpha is equal to 0. Then suppose that this guy is not there. Suppose this B2 is 0. Then you cannot decay more than the power 4/3. 4/3 will appear everywhere. Then solution, suppose that you have this. Suppose that you have B2 identically 0. That means for a bounded potential, if you have a solution of this, B bounded, real valued, then the solution cannot decay with power 4/3 and arbitrarily large lambda. For all lambda, that implies that you see. Okay? The other extremal one is the other extremal case. If you take alpha equal to 1/2, we cannot take that here. But we can take, this is a second remark, alpha equal to 1/2 allowed if you put the decay here if you put this, let's say, let's write. You have, when alpha is equal to 1/2, P should be equal to 3, right? P will be equal to 1. Then this is not allowed here. Well, if you take alpha to be equal to 1 plus half plus epsilon, P equal to 1 allowed. If you decay a little bit more than 1/2, then you cannot, then you accept P equal to 1 here. That is not part of this scale. You have to ask for a little bit more decay when you reach 1/2. Okay. Then these are the two extremal cases. If you accept to have decay a little bit more than 1/2, P equal to 1, it's okay. We are going to give two applications of this. And one application is the mesh curve result that we already talked about this, we will record. And the other one has to do with what is the structure of the blow-up in the critical case of this semilinear Schrodinger equation. Okay, we will get to there. Let's prove this. Okay, is that clear that 4/3 appear naturally if the potential doesn't decay? If you want to reach P equal to 1 here, then you have to allow the potential to decay a little bit more than 1/2. Okay, proof. Let's go to the proof. And then we go to the applications. The proof is much simpler than what we did last time, but let's go by step. Proposition 1. Suppose that S is a symmetric operator time independent. Suppose A is skew symmetric. It can depend of T or not. Suppose that, therefore, for all T1 larger than T0, you have that the integral between T0 and T1, this is an abstract result, is commutated with A, F conjugate, dx dt, plus integral between T0 and T1, integral of S of F squared, dx dt, is less than or equal to this. Okay, this is an abstract theorem. You are not saying, suppose that F is sufficiently nice, suppose that you have a symmetric operator, A is Q-symmetric, and that you are not saying which is your equation, nothing. This is something that is true in general. Okay, let's prove this. You have this inequality. This commutator applied to F multiplied by the conjugate integrating space and time plus the symmetric operator L2 north squared in space and time is bounded by this expression and this expression. Okay, let's prove this. Proof of proposition 1. Okay, you start with this. You have this, the inner product of S applied to F multiplied by F. Then you're going to pass the derivatives inside. This is the inner product of this quantity with the conjugate of this. S doesn't depend of T. Then this is this. Because S is independent of T. Then you're going to say, oh, but this is exactly equal if this is symmetric, then I can pass to the other side. S is symmetric, then I'm going to write this in this way, dt of F minus A plus S of S of F plus S of F, St of F minus S. And then you subtract this quantity you added. Okay, the first part is twice the real part of this quantity. What is the second part? The second part, you have this expression and his conjugate, then you take the real part. Then you have S. If you split this in two pieces, this is S of F multiplied by S of F, then you have twice SF, SF, plus AF, SF, plus SF, AF. I mean, this is the same trick that we have done 20 times. Is this clear? this algebra? What is this? If you pass S to this side, you are symmetric. You have S, A of F, F. And here you pass A to the other side, you are skew symmetric, you're going to have minus. Therefore, these two terms give you the commutator. Therefore, you have finished with that. dt of SF F is equal to twice the real part of ST F minus A of F minus S of F, S of F, plus twice S of F, S of F, plus the commutator Okay, now which part you want to be positive? You want this part, right? Okay, therefore, if I integrate here in T, I pass this to the other side and I integrate. I use the fundamental calculus theorem here and bound the evaluation in T1 and the evaluation in T0. Therefore, if I do this integral, I have this twice integral between T0 and T1, twice integral of SF squared dx dt plus integral between T0 and T1, integral SA F conjugate dx dt. This is going to be bounded by the integral of this, pass to the other side and put the absolute value, right? And the integral of this. Then I use the fundamental theorem of calculus here. And the integral of this, I'm going to bound this part using Cauchy-Schwarz, is the absolute value of this multiplied by the absolute value of this. Then I'm going to use that this the real part of this twice is less than twice the absolute value, or minus, plus or minus, doesn't matter, is less than twice this. The node of this guy, the node of this guy, and this is less than twice this one. Then this one, the square, plus this one is square. No, SF. This is SF here. This is SF here. This is SF. Okay? Then you have this integral. Okay? And then this integral that you pass to the other side with a minus, and you have this. You have the integral of this. And then you have the integral of this. Okay. You bound this part by the absolute value of the evaluation in T1, the evaluation on T1. You cancel one of these with these two that you have here, and you finish with what you want to prove. Right? These two cancel this one. You have what you want here, and this is bounded by the absolute value of the evaluation in T1 plus the absolute value of evaluation in T0. You can be crude there. Okay, then you have this estimate. Okay, we have one more estimate of this source that doesn't look that you're going anywhere, and then we are done. Any question? Let me write this formula here because we are going to use it now. dt of s f f is equal to twice the real part of dt of f. Okay, then we can erase that. See, we need to use the time, that the time is infinity to get our result. And this is one of the ideas, that you're integrating in the whole interval, and there is no restriction whatsoever. Only this part bothers you. Of course, the commutator will be positive. You will see it in a moment when we choose the right things. Okay, proposition 2. See, we can. Proposition 2. Take this function. Suppose that t is positive. You have any t more than 1/2. Then you take the interval t minus 1/2. You define this function. T minus 1/2 t plus 1/2 minus t. This is the function that is defined everywhere. This is your t. This is t plus 1/2. This is t minus 1/2. You are 0 here, and you are 0 there. Therefore, the derivatives of this is bounded everywhere in absolute value by 1. The second derivative of this is all the time equal to minus 2. And that's it. Okay? Then you have this function is defined here. Eta is defined in t minus 1/2, t plus 1/2 into R. I have all these properties. Then the proposition 2 is that you have this estimate. The integral between t minus 1/2, t plus 1/2, integral of this truncation in the time variable multiplied by what is positive here, that will be positive, s of f squared plus the commutator between s and a of f conjugate dx dt plus the integral t minus 1/2 f squared dx dt. All this is going to be bounded by maybe 8 t dt of f minus a of f minus s of f squared dx dt plus 8 times the absolute value of x t squared dx evaluated in t minus 1/2, t plus 1/2 absolute value. This is now you are truncating this. And you have this part that is going to be almost positive and this end, and you want to know how it changes in an interval of length 1. Why do you have all this? Okay, you will see that what your problem is, this quantity will be almost positive. This is positive. You have control of this. What you don't have is control of S of F. You have control of F, but you don't have control of S of F. But This part is going to give you the control of S of eta you need. And this is the L2 norm. Okay? Let's prove this, and we will be done. Okay, this is a little bit, okay? This is only two. After that, everything will be fine. Okay, now proof of proposition 2. Then you take the derivatives of the L2 norm of f is dt of f plus f dt of f. And then you're going to add and subtract as before. This is going to be dt of f minus a of f minus s of f plus f dt of f minus a. And now you have to add this. And this is equal to twice the real part of dt of f minus a of f minus s of f. And now you kill a is skew symmetric. Then when you this part, when you apply the a by itself, you split this into pieces, disappear because it's skew symmetric. Then you have twice sf by f. Then you have proof that this quantity equal to this quantity. The A doesn't, A by this. Is this clear? Then we have proved this. Okay, now we are going to multiply by eta and integrate by part. Multiply the above by eta prime of t and integrate between t minus 1/2 t plus 1/2 dt. Okay? Okay, then what are you going to get? Okay, let's do the pieces together in this side. Let's do this part. Then we have integral between t minus 1/2 t plus 1/2 of eta prime of t dt of ff dt. This is going to be equal to then now you pass this derivative here, but then you have the second derivatives. The second derivatives in t, this. Okay. But this is exactly equal to phi prime of t, f times f. The second derivative is minus 2. Then you have plus 2 integral of the L2 norm of f times f. Okay? You will see that everything appears transparent when you are doing the proof. The problem is that you write things to make it simple and doesn't look that you're going anywhere. Okay, this is the first one that we integrate. We integrate multiplied by this one. Let's multiply by this one the derivatives. Okay, this is a term 1. The term 1 gives you this. The term 2 is going to be twice the integral between t minus 1/2 t plus 1/2 phi prime of t, the real part of all this, right? By integration by part, this is going to be twice phi of t real of all this. But phi, or eta, eta, vanishes here and vanishes here. Therefore, this part disappears. Okay? This part is going to disappear. Then now you pass the derivatives to the other side. Twice integral t minus 1/2 t plus 1/2 eta derivatives of the real part of all this. No. Let me 1 second. No, I'm sorry. This is not, we don't need to do this one. We are going to handle that one. Okay. We don't need to do this one. This is the one that we have to do first now. I'm sorry. Okay. I apologize. This is 1 is equal to 2, so I have to do this one. Okay, 2. 2 is the integral and okay, this is exactly the same business. This is going to be 0 because u vanishes. Eta vanishes in the extremal. And now you pass the derivatives to the other side. Minus integral eta derivative with respect to t of sf f dt. Okay? This is 0. Therefore, this is equal. You have the minus here, and now we are going to use this formula. Okay? Then this is equal to minus eta of twice SF plus the other part that is the commutator SAFF dt plus the other part. Twice the real part of STF minus S of F. Okay. Then 2 is equal to this, 1 is equal to this, and we leave the other one. I think that we don't have to use this anymore. Okay, then what do we want? We want to get this part positive in the side. Then we have this part that is okay, that is 1, and have this sign. We have 2, the part that we want but appear with a minus sign. We pass this to the other side. Then if we put all these things together, we are going to have this. That gives us twice the integral between t minus 1/2 t plus 1/2 of this L2 norm plus this part that is also positive that appear in the other side. And this there is a 2 here. Remember that there is a 2. Then if we want to be very careful, we have to put this 2 here, this 2, 2. And then there was another 2 there. Okay, it has to be 2. Then it's going to be plus 4 t minus 1/2 t plus 1/2 phi of t S of f dt plus twice then the inner product between the commutator dt. Okay, I put this one here, but remember that this one is in this side, I pass to the other side. Then what do we finish in the other side? In the other side, I pass this one with absolute value. We have this, what is the derivative of this function evaluated in 1 is less than 1. Therefore, this is going to be the absolute value of this. Then is the absolute value of f x t squared dt dx t evaluated in t minus 1/2 or t plus 1/2, all this in absolute value. Okay, this is this part that we stay in this side. This part we pass. This one we already handled, this is 1. We have this term that appears in the other side, plus twice the real. Then we have twice 4 real part of STF minus SF S of F dt. And now we don't need this formula anymore. Okay, we are handled 2 and 1. We need to put the 3 that still stay in that side. Plus twice the real part of STF minus A of F minus F of F, F dt. Do you agree? This one? Okay, put absolute value. Okay, you can take the real part out and put absolute value. Everything go to the other side. Okay, what is exactly that we want? We want this, only this part to appear. Forget the real part because you put absolute value, you can forget the real part. You can forget even this function, that this function is bounded by 3, 4, I mean, how tall is this function? 1/4? I don't know. This function is, okay, how big is this function? What is the value at the middle point t? It will be t minus, it is 1/2 multiplied by 1/2 is 1/4. Then this function is bounded by 1/4. If you care, then you can bound this. Then I erase this one. Doesn't matter, you're not going to have this. Then this is true. Okay? I mean, if you want to be very picky, you put 1/4 there. Okay, then what are you going to do? You have this part. Oh, maybe I was too optimistic. Let's leave this here. I was too optimistic. Let's leave it there. Okay? And I put the 4 here. Is that okay? Okay, what are you going to do? You're going to bound this. You're going to bound this in this way. This is dt of f minus a of f minus f of f, maybe with 4 plus 1/4 of s of f squared. And you're going to bound this, all this multiplied by eta. And you're going to bound this by the same business, eta multiplied by dt of f minus a of f minus s of f squared, maybe with a 4 and then 1/4 of f squared. And what do you do with this part? This part And this part is going to be absorbed by this and this. Therefore, when you split this in this piece, this is the square of this. You put a 2, 1/4 of this, the square of this, and you put a 2 and the quarter of this. Therefore, this part will be absorbing. This part multiplied by eta is something that appears here with a number that is bigger. This part multiplied by eta, integral in t, is something that appears here. Well, it doesn't appear here, but eta is bounded by 1/4. Then this wins against this. When you came with all this, what is the only thing that stays? This part and this part. And this is what you have here. If you do it careful, you may get a or 4, a number there. Doesn't matter. Then the only part that remains when you do all this is this quantity that is here, and this quantity that you have there. And for this quantity, you put eta equal to 1/4 or equal to 1, and you get it. Then we have proved this. Is this okay, the proof? The only thing that you are doing is multiplying a, b twice is equal to 2a, b half, and then you do the square. This is 4a squared plus b squared 4. And then this part you can be absorbing the other side. This part can be absorbing the other side. For this one, you preserve the eta. For this one, you don't need the eta, and you have this. Then you have proved this quantity. Nothing deep. There's nothing deep here. Any question? Is this okay? Okay, now the proof that is, and you will see why the 4th, 3rd appear everywhere and all these things. Then we finish the technical part. All these things now will be simple. Okay, I don't think that. Okay, proof of theorem. Okay, first, assume that this B2 is 0 for the moment, and you will see that we will insert that in the general proof. Take phi, a function that has satisfied the following. It's a C4 function, is radial, strictly convex on compact set, such that it has the following property. Phi of r is equal to r to the power p plus beta for r equal to absolute value of x larger than 1. Is 0 at 0, is always positive, except in 0, and is bounded by You would love to say that your function is r to the p. But p is a number that is first is between 1 and 2. Then it will not be C4. You will have problem of singularity there. Then you have to glue things in the right way. Why this function exists, we will, if you want, we will discuss later. Okay? Does this work if p is equal to 1? Well, certainly no. If p is equal to 1, this function is not convex. P has to be more than 1. If you grow linear, you're not going to be strictly convex. You're flat. You need something, okay? Then this proof only works for P equal to 1, larger than 1. That's the reason that you need something extra for P equal to 1. Okay? Okay. Some computation. Let's do some computation here. Observe that the second derivative of phi is going to be equal, the matrix of the second derivative is this. Is the second radial derivative, this is a radial function, xj, xk, r squared, plus the radial derivative over r, delta jk minus xj, xk, r squared. Okay. How you prove this? The only thing that you are doing is saying if I take the derivatives of this function that is radial, this is the derivative with respect to r of this, dr with respect to x sub j, and this is dr of e x sub j over r. And now you take another derivative, and you're going to have two pieces. This is when you take the first derivative. And now you're going to say I take x sub k, x sub j of r. Then you're going to have this. When the derivative hit here, you're going to repeat your business. And now when the derivative hit here, you're going to have dr over phi, the derivatives of this with respect to k. And then you're going to have some delta here, jk, over r, and then the derivatives of this one that is going to give you xk, r squared. Something like that, right? And then you take r. Okay, let's do it with careful. This is this. And when you take derivatives of this one, this is, okay? I mean, if you're computing the matrix of the second derivatives of this radial function, you have this. In particular, is this clear? If you multiply the gradient with the second derivative matrix with the gradient in this side, what do you get? You can see that you're going to have a cancellation, and you're going to finish with this. If you do this computation carefully, you're going to see that you have some cancellation. Okay? Suppose that you multiply this by dx sub k of phi, second derivative k, second derivative j, dx sub j of this. Do that and use this business, and you will see that you will get exactly this form. I mean, it's a... Do we accept that, or we made the computation? Huh? Huh?
When you derive 2 times phi, the last term is not over S2.
Okay, let's see. You have, what is the derivative with respect to x sub k of 1 over r? I mean, the homogeneity of this is minus 1. The homogeneity of this is 0. The homogeneity of this is minus 1. It's okay. It's okay? Okay. Then what you're going to do is to multiply. You're going to multiply this formula by this one. dr phi xj over r, and from the right and this from the left. And when you do that, you will see that you will have the square here, and this part will cancel, and you have exactly what you want. Okay, if you do the computation, you get this formula. And now, how big is this? Well, for this is equal, if you are r to the p, when you take derivative, you don't see this beta. This is going to be x. Now you have p, and you lose 2 powers. Wait. This is a square here. I'm sorry, this is a square here. Okay, let's do it because now I mixed up things. I have to do it because I mixed up. Okay. Is this clear that this is the second derivative? I'm going to multiply this formula from the derivative with respect to x sub k from the right and the derivative with respect to x sub j from the left, or the other way around, doesn't matter, symmetry. When you do that, what do you get? You get the second derivative, this one square, and now you have xj squared, xk squared, r squared, r squared. This all addition of this gives you 1. What do you get here? You have this, the radial derivative cube, and what do you get here is delta jk r xj xk r cubed, and now you have xk xk r squared. When you pass this part, it's going to give you x sub j squared over r cubed, and this one is going to give you x squared xj squared to r phi. And you see that when you add it, you're going to have 1 over r minus 1 over r. And this is give you 0. This gives you 1. Then you finish with this formula. This is the matrix. This is the gradient from the left, gradient from the right. You get this. Is that okay? Okay. Now, how big is this expression? This is r to the p, and now we are okay. You have, this is like for x equal to r larger than 1. This is r to the p, but you take 2 derivatives. This is p minus 2. This is r to the p minus 1, but you multiply by 2. Then this behaves like r to the 3p minus 4. That means that this is equal to 1 over r4 minus 3p. You say that 4 minus 3p start to appear everywhere. 4 and 3 start to appear everywhere. Okay, this is the reason. Okay, but that doesn't prove anything yet. Okay, all this is out. Okay, we have the radial power function. Okay, where are we here? We have all this computation and and in fact, the second derivative of phi as a matrix is larger than p minus 1, identity for x more than 1. If you compute the second derivative matrix, you have that you are larger than this. I mean, you take 2 derivatives, and you're going to have something like that. Okay. Now, you are going to say that f is going to be the solution exponential lambda multiplied by your function, that is the choice that you have multiplied by your solution. Therefore, what is the equation that f satisfies? Then f satisfies this equation. Then you have that u is e to the minus lambda x multiplied by f, and you realize that you have this equation. E lambda f dt minus I Laplacian of u that is equal to this. Where S is the symmetric part that is minus I lambda 2 gradient of phi gradient plus Laplacian of this. A is this part. If you want, this is this equation, dt of f minus I Laplacian of f minus 2 lambda gradient of phi gradient of f plus this is minus Laplacian of phi minus this is when you pass, this is minus, this is going to be lambda Laplacian here plus lambda square. This is lambda square, gradient of u square, maybe with a minus. Okay, let me see, this is plus lambda square, minus, and this is a square here. Okay, this is the equation. What is the equation that this function satisfies? It satisfies this one. I b x t of x. You change variable u by f, and this new function f satisfies this equation because the Laplacian of this gives you terms, this one, and this one. And of course, you have to start that you satisfy this one. Is this clear? Is this clear that f satisfies this equation? Remember that you have the dt of u minus I Laplacian of u plus IB xt u. And now switch u by f, and you will see that you will finish with this. Now you factorize this part into the symmetric part, that is this one, and to the skew symmetric part, that is this one, and you still have an inhomogeneous part, that is this one. And S, because the exponential function that you have here only depends on x, there is no t involved, this S doesn't depend on t. Okay, that is one of the hypotheses here. In our previous class, that was time dependent. Okay, what is the commutator of these two quantities? We have done this. The commutator of this will be equal to this one, minus 4 minus lambda, 4 gradient, second derivatives of phi, gradient, minus 4 lambda square, gradient of phi, second derivatives of phi, gradient of phi, plus the Laplacian of this. This is a computation that we have done several times at this stage, and it's simple because this function phi is independent of time. It's simple. Okay, look the commutator. There is a minus here. When you integrate by part, this is going to be positive because this gradient, you are going to apply this to f, and this one will come integration by part. When you do this, what will you get? dx. You're going to get, for integration by part, you have this gradient of f, second derivatives here, Then you have minus, minus, you have plus 4 lambda cubed, all this. F multiplied by F plus or minus lambda this. F multiplied by F. This one, you integrate by part, pass the gradient here. You have this part is second derivative of phi this square dx. This is going to be what you, the thing that you compute before. And now you don't have any idea, this may not be positive. Okay? You see that the commutator have this part is positive, gives you control of the gradient. This part is positive, gives you control of the L2 function. And this part that is not positive that you have to handle. Okay. Okay, I have to erase the theorem. I'm sorry. This is the only one that I can erase. No, in fact, maybe let's see. Okay, let's see if we can avoid to erase the theorem. Is this clear that this is the equation? This you split this into the pieces and you have this commutator? Okay. Step 1 of the proof, we are going to prove that there exists a sequence of time that goes to infinity such that the supremum in J of this S of F of x dj square dx is finite. Okay, let's call this number C lambda 0 this number will depend of C lambda, the L infinity norm of this, the P, and so forth. What I'm saying is this. What is your hypothesis? Your hypothesis is that this function that you have here is in L2. You take the square. Maybe you need to put a 2 here that is not going to change anything. You take the square of this. You are in L2. And what is your claim? That is not that this function f is in L2, is that S, the operator S applied to f, is in L2 in some times. Why do you want this? Because you need to kill this part. You're going to apply this theorem, and you have to kill this part. Up to now, you only know that you can evaluate this. But you don't know if you can evaluate this one. Okay, how do you prove this? Okay, look here. Look, take proposition 2. If you go to proposition 2 and you want to apply proposition 2, forget about this part that is positive. You get rid of this. Forget about this part that is positive except this part. I have to handle this part. Then the only thing that I have, if I use proposition 2, I only concern with this, I have this. The integral between t minus 1/2, t plus 1/2, for any t larger than 1/2, integral of this S f of xt squared dx dt is less than what? This part is positive, okay, but you have a piece that is not okay. You have to pass this to the other side. Then this part is positive except for this piece that you pass to the other side. The second Laplacian of this L infinity, this f squared, integral between 0 and t. This is the have this piece that is not positive that it has to pass to the other side. Then I have this. I took the L infinity node of that. This is independent of time, and I have the L2 of this. I'm taking this part, the positive part I can throw it away. The part that is not positive I pass to the other side. This part is positive, I throw it away. What is this? Well, this is, you have this equation. This is dt. This is dt of f minus a of f minus s of f equal to I b x t of f. Therefore, this part is what? This is b. Forget the I. There's a square here. This is less. Plus 8 L infinity nor of b in L infinity square f square. Plus this quantity. Okay. Now, how is the second derivative of this? This is the second Laplacian of this. The second Laplacian of this function, where is our function like this? How big is p? Well, p at most will be 4/3. Is that okay? P at most will be 4/3. If you take 4 derivatives of this, you're going to have power that is negative. This is bounded. The 4 derivatives of this function is bounded. Then this quantity is bounded. This quantity is bounded. This is hypothesis for you. Then this is exactly that you know that you are in L2. All these are in L2. This is in L2 supremum in time. And you are integrating in an interval of length 1. Therefore, this is bounded, this is bounded, this is bounded, and you have that this guy is bounded. Because you are integrating in length 1. And you can change here this quantity. All this will be less than this. This number that you have here, lambda, the Laplacian of this, L infinity, the L infinity nor of the potential square multiplied by C lambda, maybe multiplied here by 2 C lambda. Then you have bound. You have bound this quantity by this number. It's okay? This is the L2 nor. Remember, F is this. Your hypothesis is that F is in L2 at any time and uniformly. Then this gives you the L2 in some point. This is an interval of length 1. The L2 supremum is bounded. You change this L1 by L infinity, and you have this. Okay. But let's be careful. You want to bound this supremum in one time. And you have only bound this in the integral. Okay? We need one more step. Okay? Let's go here. What do we know about this function, eta? Eta was like this. Then if you move between eta minus 1/4, between plus 1/4, you have that this quantity is more than this. Instead of integrating in a larger interval, something that is positive, I integrate in a smaller interval. But if I am here, this function is bigger than a constant. Then this quantity here is bigger than some constant that happen to be 3/16. Then in this interval, you have a lower bound. It's 3/16. Therefore, all this, you can forget this part and put, this is more over 3/16. And now what do you have? I'm integrating a function, right, in the whole interval, and this is bounded. Then you take the average, you multiply by, this you have 3/16. This length interval is 1/2. You divide it by the 1/2, and then you have, is the integral, is the average of this function is bounded, then the function has to be bounded somewhere by the same bound. Then what I'm saying is this. I'm not saying anything deep. I'm only saying that now I am into t minus 1/4, t plus 1/4, 3/16 integral of s of f squared x t dx dt. Is this okay? I integrate in something smaller. In this part, this function is bounded below by 3/16. Okay? Therefore, in this interval, I can put 3/16 here. The length of this interval is 1/2. Then I divide it by 1/2. I multiply maybe by 32 here. Then you are saying that this is the average. You are integrating in an interval of length 1/2 and dividing by 1/2. Therefore, if this is bounded by that number, in the average, it has to be bounded somewhere by that number. Therefore, there exists a time between minus 1/4 and 1/4 where this is less than the number that you want, that you have there, multiplied by 32 divided by 3, something by a huge number this other side. Then you have proved that. Each time that you have an interval of length 1, you can pick up a point where you have this bound. And of course, this may depend of this lambda here that you have. Is this okay? Okay. Well. Okay. Please, if it's something not clear, you have to tell me. Then we use proposition 2. We finish proposition 2. We don't need proposition 2 anymore. We finish the proof of proposition 2. Okay. Then we have this. Depend of maybe on lambda. Okay, what's the step 2? Step 2 is that for every, then you have a sequence of time that goes to infinity where this is true. Then for all j positive, you have that the integral between t1 and tj of this quantity, e2 lambda phi of x u of xt squared 1 plus x squared 4 minus 3p over 2 dx dt is bounded by some where c lambda depend of c lambda that is your part of your hypothesis. May depend of lambda, the L infinity nor of this, the p that you have chosen, the alpha, whatever. Okay. Now, let's assume this and finish the proof, and then we prove that, because otherwise you could be completely discouraged. Then for all practical purposes, we know who is our function, and so forth. Okay. Assuming this, step 3, assume this for the moment. Let's prove the theorem. Proof of the theorem. Of theorem 1. And you will see that this is the only moment that we have used that you preserve the L2 norm. What is T sub j minus T1 L2 norm squared of? This is exactly the integral between T1 and Tj of u of xt squared dx dt, because you preserve the L2 norm. You can put here 0 if you wish. You preserve the L2 norm. Okay, write this in this way. This is equal to T1 Tj integral uxt square e lambda square x like this means 1 plus x squared 1/2. Then you put x to the power 4 minus 3p. You have x to the power 4 minus 3p. You have e2 minus lambda phi dx dt. This quantity certainly is equal to this quantity. Take the L infinity out here. This is less than the supremum in x of this quantity multiplied by the L2 norm of all the what you have. What do you know? What is the supremum of this quantity? This part at infinity decay exponentially, and this part may grow or not, doesn't matter, because this part killed this. Is this clear? Please.
F or U? Is it F or U?
U. No, I say that I am assuming that I prove this, and I finish the theorem. Okay? From here? This is because I am assuming that, the U, since this is real valued, it preserves the L2 norm. In some moment, I will have to go from F to U. Right? Up to now, we have a step 1 is this one. Okay? In some moment, I will go from F2. But I'm assuming that this is true. If this is true, then I use that L2 norm is preserved. I multiply and divide it. This quantity is bounded, certainly. Suppose that, for example, that P was 1, and this will grow linearly, but this decay polynomially, exponential of the polynomial, then certainly this is bounded. This is bounded. Then you have this is strictly bounded by a number here, and this is another number. Then this is bounded by some number here. And you are saying that this quantity multiplied by this quantity is bounded by a fixed number. And who is Tj? Anything you wish. Tj goes to infinity. The only way that this is true is if this is 0. And you have finished. Then if I prove this, I prove the theorem. Okay? Then take, this is fixed. This number is fixed. The pen of lambda, the pen of the L infinity nor, the alpha, but it's fixed. Take now Tj goes to infinity, then you have bound. This goes to infinity, multiplied by this, is bounded. Therefore, this is 0. Imply that U0 is 0. Okay. Then we need just to prove this quantity. We just need to prove this step 2. Okay? Then can I erase the proof of the theorem? Is that okay? Can I erase it? Okay, look, proposition 1. What proposition 1 tells you? That for any time larger than t0, the integral of this quantity plus the integral of this quantity is bounded by this one. Now, look here. If I take Tj here, Tj here, Tj here, then this will be Tj and this is T0. How big is this? You can use Cauchy chart. This is the L2 nor of this multiplied by the L2 nor of this. The L2 nor of this is bounded. The L2 nor of F is bounded because this is exactly equal to say this. Supremum for all time, this is F of x t squared dx. This is equal because, you have defined f accordingly to this. And there is no difference between this function and this one at infinity. The only difference is for x less than 1. And for x less than 1, this function is in L2 and all this in. Then this is equivalent to this. Therefore, this part is bounded. The L2 nor of this, the L2 nor of this is bounded, the L2 nor of this is bounded, the L2 nor of this is bounded. Then, using this part and using the hypothesis, all this is bounded. Then this is like if they were not there. You can forget about this. They were not there. Then everything will be, if the positive part of this, that is this one, a piece of the commutator can control this one. Okay? Okay, then what is the good thing of the commutator? What you have here written is this. The commutator has a good part that is this one that gives you control of the gradient, that is this part that gives you control of this multiplied by this, and since that this is wrong, then you have a competition between these two pieces and this one. Okay? And you can forget about this one because this is not going to help you now anymore. Then your problem is, I'm going to use this proposition, I forget this part, and I'm going to write what we have. We have the integral between T0 and T1, and now we have this part, 4 lambda, integral of the second derivatives of phi, gradient of f squared, okay, I will write it like this, dx, plus this one, 4 lambda cubed, gradient of phi, the second derivative of phi, gradient of phi, f squared dx. This part we don't have control, will pass to the other side. This part, dt, is bounded by this integral between t0 and t1. This part that we don't control, L infinity north of this, f squared dx, plus, who is this? This is the b, right? This part is b. Then this is b in L infinity, b, f squared dx dt, and here you have this part, t0. Okay? This is, let me put it like this. Okay, then I have, okay, then I have another. Is this okay? We have this. I mean, I remove this part that doesn't bother you. This part is positive. We can remove that. This is bounded. This is still, there is a number here that depends on C lambda, the hypothesis. Right? And we have this. Then, do you believe this part here? Okay, we can kill this part. Okay. Now let's go by pieces. What happens if x is larger than 1? If you want, I will put the L infinity north here. I will put lambda, absolute value of the second derivative here, the integral in x, the integral in time. Okay, dx dt. If x is larger than 1, look only this part. How big is this? Look the term 1. 1, the third one is larger 4 lambda cubed integral of what? This is going to be like, this is like x to the power, remember, for x larger than 1, Cora, erase, since you have phi of x is x to the p plus some beta. Therefore, the gradient of phi is x to the p minus 1, and the second derivative, for all practical purpose, for x more than 1, is x p minus 2. Therefore, all this is like f squared x power 3p in the 4 minus 3p dx dt. If you want one before integrating by time, before time integration. You have this, right? You have this part. This gives you some power. This gives you another power. This gives you another power. You have this. Let's say that this part by itself controls these two. How this one decay, the B? Okay? And now let's see that we have, this was the inhomogeneous term. In this inhomogeneous term, B has to be squared. Remember that this term is coming from St of f minus A of f minus S of f squared. And this is the square of B and the square of f. Okay, how is the square of x and the square of the square of f, since we don't have the B2, it has this hypothesis. It decay like 2 multiplied by alpha. Then let's go here. This is like C1 x to what? 2 alpha, right? Because you have the square. 2 alpha. What is 2 alpha? 2 alpha is exactly equal to 4 minus 3p. Therefore, when you multiply this by f squared, you have this. Why, when you integrate here, this part controls this part? Why? If both have the same decay. Because here you have lambda cubed, and you can take lambda sufficiently large. Then a fraction of this kills this part. Then for x larger than 1, this part is less than a fraction of this one. What about this one? Well, since phi is like x to the p, then the bilaplasian of this is going to be x to the p minus 4. This is bounded. Then this is, therefore, this f squared multiplied by the bilaplasian is going to look for x larger than 1 like f x to the 4 minus p. And you can see that this part decay better. This is decay much stronger. Then this one is already controlled. This gives you a stronger decay than this one. Then this part controls this and this. Therefore, a fraction of this will give you control of this. This is for x more than 1. But remember that this part of your function is only valid when you are more than 1. Okay? Okay. Okay. Now, what happens if you are, for any epsilon, now go here and you say, for any epsilon positive, what happens if you are in this interval? You will be able to say, well, I will have some bound here that will be bad, but I will be able to kill this with lambda cube. This, right? Then you can extend this idea to to any epsilon, but you will have to pay with a very large lambda because now you are not going to say that you control this using the lambda. You cannot control powers anymore. Okay? You are going to use that the function here is convex and have this. Now, what do you do for x less than 2 epsilon? Now you use this part. You haven't used this part. This is going to be Poincaré inequality. What do you mean Poincaré? You have this. Okay. This is bounded. This is bounded, and close to 0, you can say that this is, since you don't have control, it will be a number. This will be control, you have a number. You have this. You have, I need to control this close to 0. I have a number in front. I can say that this decay only for x large. It will not be decay. It will be bounded next to 0. This is bounded. I cannot say that this decay next to 0. Then I have to do boundedness. Then I have this is bounded. Right? Okay, how you use this? Take a function 1. Take a function that is equal to 1 if x is less than epsilon and is equal to 0 if x is larger than 2 epsilon. Right? And I want to bound this. I want to bound what happened next to epsilon. Then this is equal to this. And take this function. Okay. But now, Poincare inequality tells you that you can control if a function vanishes on the boundary, that this does because you have this is equal to 0, you have that this is less than the gradient of this. Right? But you have to multiply by the diameter 1 square root, and then you have this square. This is Poincare inequality. You have to multiply by the diameter of the domain, but since you are not in L2, you are taking the square of this, you need to put a square here. Okay, now take the derivatives of this piece. This part has two pieces. Epsilon squared, multiply it. When the derivative hit here, then you're going to have theta. Theta is a function less than 1. You're going to have this. And then you have when the derivative hit the derivative here, this function go between 1, then the derivatives of this function is like 1 over epsilon. Since you have the square, you lose the epsilon. But now you are here. Then you can put the epsilon here if you wish, and epsilon squared. Okay, what do you do with this piece? You can handle this piece exactly like before because you are not approaching, you are far from 0, and you can kill this part using that you have a lambda cube here, and you only have a lambda here. Everything is bounded. You have a lower bound here as far as you don't reach 0. Because you are convex, right? Okay. What do you do with this part? Now, this part gives you a bound of this term that you have in this side. Remember that we only need to bound this part. We have bound this. We want to bound this. Now it came out that we need only to bound this part. Okay? Then we don't have any of these things. Look what you have here. This function is strictly convex. Phi is strictly convex in a compact domain. Then you take on the unit ball is strictly convex. You have that this quantity right, is larger than this sum. Right, when C rho uniform in the unit ball. Then that gives you control of this part. This part gives you control of this, and you grow like lambda. And at the end, you have a 4 lambda in the front. What is the bad term here? The bad term here, you have the L infinity node of this, give you a big constant, a lambda, and give you this. And you have to control I mean, you have x less than 2 epsilon. How this one is going to control this is you have this lambda here, and you have the same lambda here, because you have this epsilon here of the Poincare. Therefore, always this part plus this part control this. Therefore, this is a priori bounded. And what is this? Then you have proved that this is a priori bound. What is this at infinity? Therefore, after all this, you have seen that this part that you have here is bigger than this. Then you have a constant. Everything will be bounded by this constant that was the one that you used to kill the integration. Therefore, you have these quantities bounded. T0, T1, F, and since you only care what happened at infinity because you are in L2, this is like F is this. What is this? This is like x to the power p 3 times, and you have 4 derivatives. Since minus 4, you have this in the bottom. X to the power 4 minus 3p. But you only care what happened at infinity. You can write this like this. Then you have proved this. In the moment that you prove this, you finish. Okay. Okay. Two things. One thing, how you insert this here. How do you insert this part? Well, you insert this part writing this as a part of the symmetric operator. You write A, then you're going to have here, this is B1, and B2 will be written here. If you want to include B2, you write this is I, B1, X, T, F. And I have here minus I, B2, X, T, F. And here you have, this was F, this was F. Okay. Now this part is going to be real with coefficient in front that is real. This is going to be part of let me see. Where are you going to put the B? Is 7. No, I cannot put I here and I here. It has to be like this. Therefore, this part, and this is plus, is going to be, this is part of your skew symmetric operator. Okay. And you include that in the commutator. And when you include that in the commutator, then the part that is going to appear is going to be the derivatives, radial derivatives of this, because this is going to be multiplied by something like this. And then only the negative part play a role, and this is why you have this. And you have, it's easy to compute this, and it's one of these two numbers. I don't know. I didn't do that. Okay. Then you can see that there is nothing hard on the proof except that it's long. And it's again, the commutator gives you the things, and you have the trick to kill the integration by part term that involve S of F, and you only have control of F, and so forth. Okay, the next time, we are going to apply this problem and to recover the Meshkov result, and we are going to study how can you use this to prove that in the critical L2 case, for example, when you have the focusing Schrödinger equation in the critical case, L2, you can cook explicit example of the blow-up. We will explain that in the whole case. Then how is the blow-up? It has to do with the ground state. That is a solution of the elliptic problem. And you know exactly how these things behave because you do everything explicit. And now the question is, suppose that you have blow-up that is exactly concentrating, but you cannot have explicit things. I mean, you can have many solutions that are going to blow up that are not explicit, that you cannot. Can you have the concentration be faster than exponential? Can concentrate, for example, Gaussian or something like this? What we're going to prove no. Is that all the concentration at most can be linearly exponential. The ground state gives you the fastest possible concentration. Okay? And that will be the two applications of this, and then if time allows, we will start the Benjamin-Ono equation. That is a completely different business. Okay. I'm sorry that this sounds to be more technical than it really is, but it's not, I mean, if you go very slow, it's not hard. It's not hard. You can see that this is